So it's time to start. Okay, this is the plan of this lecture. So I'll first do the main thing, and you're going to see that this is much simpler than what you're already seeing. Right, this is much simpler. We're like moving toward the algorithms. At least like today, it's going to be simpler, and maybe tomorrow as well. And the last 30 minutes, I'm going to spend time on projects and homework. The first homework, those inequalities. Right, I promise you, talking about those inequalities. And we talk about projects at the end. Okay, so let's get started. This is about something called the proximal operator and algorithm and Lagrangian dual. All right. So I can imagine that most people might have heard of the Lagrangian dual. Right? It's not working. It sometimes works, so it's a random thing. All right, okay. So many of you heard of dual and Lagrangian dual. I think this is dying anyway. I'm not using it. But you may not have heard of a proximal operator or proximal algorithm. Some of you do, but most of you, if you are undergrad, you probably haven't heard of it. But I claim it's fairly general. I'm gonna use this proximal thing to connect lots of different algorithms to give you a simple but quick view of different algorithms. All right. So this is the idea. All right. Okay. So let's set it up. Now we're doing algorithms. Now our goal is not to analyze when this algorithm will give us a certain solution, but we're gonna just go find the solution. Alright, so we assume we have a convex function differentiable. But by the way, lots of these methods do extend to non-convex region. But at the moment, I assume it's convex and differentiable. I mean, you may actually have a doubt. Well, you're doing L1, you're doing sparse optimization. You're going to have a non-smooth. You're going to have a non-differentiable term. But for the moment, I assume it's differentiable. And you just minimize this function f of x without any constraints. Right, so x is the decision variable. Now, the simplest algorithm is the gradient descent iteration. So it does the following. Suppose you're at a current point xk. You take the gradient of xk, of f at xk, and then look at the negative gradient direction. Make a step. See the step size, and move along that step and get the new point. All right, this is the gradient descent. All right, the gradient descent looks like this. Suppose this is some kind of quadratic function. All right, you're at this point. You look at, but this is the global solution. This is the solution. This is your current point. All right, and the gradient is this. Negative f of x k. The gradient, the steep is the ascent direction. Steep is the uphill direction. Now you move along the negative gradient direction, and for certain step size. Alright, and you move to this point. This is your new point. You keep doing this. You're gonna keep doing this. You're probably doing something like this and this. Okay. Finally, you'll get there under some conditions. So, there's different interpretations of the gradient method. These interpretations allow you to compare to other methods. Now, this is one of the interpretations. So, this xk plus 1 is actually the minimizer of this energy, of this m function. This function is approximation of the original function at the current point xk. Using a quadratic function. Okay, so this is a function of x. X is the variable. F of xk is fixed. So you're looking at a fixed value plus a linear approximation. Linear approximation means that this is a linear function, and I use the gradient. I use the slope of the function, right, to approximate the function linearly, and I plus the quadratic term. Right. If I just have this term is constant function, nothing changes. If I have this term, this is the affine function. or linear function. It's a flat thing. Then I have this term. I'll keep my future term close to, because I minimize, so I will keep my next point close to the previous point. So if I draw a one-dimensional function like this, and I'm here at xk, okay, and this value is f of xk. So what I'm doing is looking at the gradient and then curve it up at a quadratic. So I'm doing something like this. Alright? Something like this. I didn't draw it very well, but no, this is the idea. And then how do you get the next point? You get next point as the minimizer of this quadratic. So you get this point. This is xk plus 1. Right. So this idea is also called the majorization. You will have to, in general, you will have to choose a proper C. In other words, the C have to be small enough so that this term is strong enough, and so that this quadratic approximation is entirely above the function. Right. So this quadratic approximation is above the function itself, and you then minimize the quadratic to get the new point. This is the same idea. This is very similar to if you're from math department, learn numerical analysis. You should have done some PDEs. This is similar to the forward Euler iteration, also called the explicit update of an ODE. But this is ODE is a different thing. ODE doesn't minimize anything. ODE just want to evolve let's say a curve. All right, this curve is called x of t. All right, you want to evolve this ODE, follow this curve, but you can't follow it at very small steps because that'll cost lots of computation. So you're going to do is at every step just look at the slope and go to this. And go to this point, you actually should stop here. You actually should be here, but you go to that point because you use the approximate gradient. And then use the slope of this point. You get this. You move another step. Use the slope of this point. You move another step. So this is forward Euler. You're tracking the curve using the gradient at the start point. This is where you start every time. This is how you go to the next time. All right. Okay. Now, very general stuff. And by the way, we're going to use those difficult to prove inequalities to show the convergence of this, to show why this converge and how fast it converges. All right. Okay. This is the forward step. Now, what's tricky is the backward step. All right. You're not using the gradient at the current point. You're using the gradient at the next point. You're using the gradient at the end point. All right. So backward Euler iteration, also known as implicit update, do the following. So this is my current point. I'm gonna take a step. I'm gonna use the gradient, but I'm gonna use the gradient at my future point. I don't know my future point because I need this gradient to calculate my future point. So my future points are equal to the current point minus the step size times the gradient of my future point. And this is the equation you have to solve. The unknown is on both sides. All right. Therefore, you solve this equation for this unknown, xt plus 1. And then you let the solution to be the next point. And this is called a backward Euler. Backward Euler is more stable than forward Euler. If you do if you do linear equations, you can analyze the stable region of backward Euler. And forward Euler is stable somewhere here, right? Backward Euler is stable somewhere here outside. Do you remember this? Have you done this? All right. So it has much larger stable region. Okay. So this is it's more computation, but it's stabler. All right. It won't. In other words, the error between this finite approximation, numerical approximation, and this true curve will be bounded under easier region, under easier conditions for backward order. Now this is equivalent to the following. You can set it up as a equation for the next point. You can also set it up as a equation for the next gradient. All right. G actually stands for the gradient at the future point. I claim the gradient at my future point is the gradient at my current point minus the actual step size, which depends on the gradient. All right. So this is exactly the same as this equation. Just do a change of variable. But once you solve for the next gradient, future gradient, you put it back. You get this gradient, you put it back, and do the actual step. The same thing. You can solve for next point, you can solve for next gradient. All right. Okay? But it turns out people also do this in optimization. I'm not using the current gradient, I'm going to use the gradient of the next point. It's called implicit gradient descent. All right. So this is my current point. I forgot to make it bold. Should be bold. So this is my current point minus step size of my future gradient. Future gradient should equal to my future point, blue x, and I have to solve for u and x. I get next point and next gradient. Okay, this is called implicit gradient descent. And C is the step size. Well, I have to say something about C. You go back to the previous slides. C is exactly length, exactly the factor multiplied to the gradient. I mean, if you choose C twice as large, you move like twice as far, right? So C is the step size. By the way, this is called step size. The norm of this thing together is called step length. It's just some terminology. But if you go to the implicit gradient method, C is no longer the step size. This is not really the step size. All right. Now you're gonna see it's very different. Now even if you put C as infinity. Now even if you put C as infinity, nearly infinity, I mean this doesn't give you like a point that's arbitrarily far from xk. It only will give you a point so that the u is small. Do you agree? Now if I put C very large, it'll force u to be small. It does not necessarily, because u gonna depend on C. You make C large, it doesn't mean C times u together is large. All right. So this is be careful. C is not step size. All right. But you see the difference. So now we're gonna analyze this implicit method. This is the key. All right. I claim implicit method is the proximal operation. What is the so-called proximal operation is the following. Suppose Z is your current point. Z is your current point, all right? You minimize our original function, but not just itself, but plus a term that's quadratic in x, and it's x minus Z 2 norm squared, with some weight 1 over C, basically. So numerically, you can think that we're minimizing the sum of two functions. We're going to try to minimize f of x, but at the same time also keep x close to z in the quadratic sense. Right. So if this function does not increase faster than this, I won't be able to directly minimize this function, right? Because this function is also strong. So this is quadratic. This grows quadratically. If this function does not grow quadratically, does not grow faster, I'm going to have to consider this. All right. Okay. So proximal means like being close. So proximal algorithm means close to the previous point. All right. So what is this problem? You take this optimatic condition, first order optimatic condition. Take this gradient. It's just 0 should be C plus the gradient of this function, plug in the solution. Solution is this guy, all right? Solution is just proximal, right? And plus x star minus z. Now I move this 1 over C to in front of f. Then I have this first order condition. If you look at this condition, it's a comparison between the gradient of the original function and this length. All right. So in general, if I were to just minimize f just by itself, I'm gonna just do this. I want to do this, but for some reason, you're gonna be clear what the reason is. For some reason, I don't do it. I don't just minimize itself. I also minimize this term, so it's a competition between the gradient and this difference. All right. So if I let the c be infinity, all right, I'm going to minimize the function itself. Right? If I let the c be infinity, this thing won't be unbounded, it turns out. Right? If I let the c be plus infinity, if this is unbounded, this will be also unbounded, so total thing can't be 0. All right. So if I let the c be infinity, actually this term will be 0. So if I let this c be infinity, this term goes away. So actually I'm going to minimize the original function f of x. All right. No, but this is if you look at this is you just turn to move things around. X star is my next point. Z is my current point. X star, you move this term to the left, move this term to the left. So X star equals Z minus C times this. So X star is the implicit point. We're doing an implicit update. So whenever you do implicit update, you're minimizing this energy. You're ignoring the gradient at this current point. You directly add a quadratic to the function. This is what you're doing. All right. So if you do implicit update, you're not adding the gradient term. You just use the function itself and add a quadratic everywhere to the function. This is what you do. This is z, and it's still doing an upper approximation, but this approximation is different. Okay. So proximal operator is equivalent to an implicit gradient or backward Euler. Same idea. Now question is, why do we do this? Do we gain anything? If you linearize this function, if you linearize this function, turn it into a linearization, it's simpler. Right? It's much simpler. But this problem is, just looking at it, it's not easier than minimize f of x original. Why do we do this? Can somebody guess?
I think the quadratic term will make the function stronger, more complex.
That's one reason. So in other words, if f of x is piecewise linear, just a bunch of linear pieces, all right, you minimize f of x may not be simple, may not be stabler. You add this quadratic function and make it strongly convex. All right, so you make it curve up more, give us a positive curvature. You guarantee it has a positive curvature. So when you minimize it, it's stabler. What's the other reason? Okay, the other reason is I can let f be non-differentiable. Here I have assumed that f is differentiable, and I derive this. But it turns out f of x can be non-differentiable. Okay, so proximal operator handles a sub-differentiable f. All right. So now I assume f is closed, proper, convex, but it's only sub-differentiable. It doesn't have gradient everywhere. And the partial f of x, this is a recall. This is a review. Partial f of x is the subdifferential of f at point x. Recall, u is a subgradient if this inequality is satisfied. So in other words, u is a support hyperplane of f at point x. All right. Now, in general, the subdifferential is a point-to-set mapping. I give you a point. You actually return me a bunch of u. It's not just one u. It's a whole set of u, right? So it's point-to-set. Neither direction is unique. So if I give you a u and ask you what are the points that have this u as a subgradient, it can be many. It doesn't have to be a unique point. So this mapping is actually neither direction is unique. Alright? But this proximal operator is well defined for subdifferential f. It is actually point to point. What does that mean? If it means proximal maps, this proximal mapping maps any input to a unique output. Here's what it means. It means if I give you a unique z, there's only one solution to this minimizer. There's no ambiguity. I give you a z, you're going to definitely return me a unique x. So this is the proximal operator. So why is it unique? Now, from a minimization point of view, like you said, this is strongly convex. Strongly convex have a minimal curvature. When you have a minimal curvature, you minimize the function, there's only one unique point. Right? So the objective of a strongly convex solution is unique. Alright. So let's look at the domain. Now, I really haven't talked about the domain of function. I assume the function is defined everywhere, but if you do have a domain, if you do have a finite domain where f of x is finite, has finite value, outside this domain f of x has infinite values, then the domain of this proximal operator is actually Rn. So in other words, I can put any z there. This z doesn't have to make f of z finite. I can put any z there. You just need to make f of x finite, and then plus a penalty. That's all you need to do, because that's finite. You can put any z here. Alright, this is also nice. And as I said, this proximal thing, is totally equivalent to other representations of the step. Right? You can write it as a minimization problem, f of x plus a quadratic term, or you can write it as the first order optimated condition of this problem, which is zeroing. Now here I have c times the subdifferential. Alright, this is a set. Because this is a set, this is not equal. The 0 is a vector within the set. This is set plus vector. This is like a translation. This is an offset to the set. Right. Okay? Or you can write it like this. Write it as solving an equation for x and u. Well, different ways to write it. Right. So what's important is this result. If you do the proximal, use a x star. If you put x star here, it returns you x star. Then that x star is the minimizer of f. Is a minimizer of f. Okay. If you put any solution, any minimizer of f, put it as z, you're going to get the minimizer itself. It's very easy to show. So you get this. So because if I put a minimizer of f as z, when I use that one, f is minimized. This is also 0. 0 is the minimum of this guy. Right? So if I put a minimizer, I definitely get the minimizer back. I can't get any other minimizer. I don't have any incentive to deviate from my point if the point is already a minimizer. Alright. Now if I put a z there and I get z, what does that mean? It means the minimizer makes this term 0. If this minimizer makes this term 0, therefore 0 is in c times partial f of z. Right? So if I put z here and I get z here, the solution is also z. Then this term goes away. 0 is a member of c times the subdifferential of f of z, which means z is a minimizer. This is first order optimatic condition. So this is if and only if. Okay. Alright. So let's move. Here are some bunch of examples. Let's do some of these examples. So the point is most time, if I put a general function there, You just put a general convex function there. Proximal operator is not easy to compute. Usually you put special functions there. Alright? So this is the indicator function. C is a convex closed set. Non-empty convex closed set. If x is in C, you get a 0. If x is not in C, you get a plus infinity. Right, this is the indicator function. So what is this? What is minimizer iota x in C plus 2 little c x minus z? So guess what this is? What is the solution of this? So I have a set C. This is set C. Inside this set I get 0. Outside this set I get infinity for this function, for this indicator function. If my point Z, my input point Z is here, what will be my solution? Z itself. Alright, solution will be Z itself. So if Z is in C, x star equals Z. Otherwise, let's say Z not in C, what will happen? If Z is here, well, first of all, can I have a solution outside the set? No, because then this will be plus infinity. There's no point to minimize it. I have a way to make it finite. I will have to make it finite. Therefore, my solution is definitely here, somewhere in C. And then, it doesn't make any difference if I'm staying in the set, because it's a 0. First function is 0. My goal is to minimize the second one, as long as I am staying in the set. The second one is distance. Right? It's 2 norm squared. You can ignore the square. The same thing. Right? So we're going to minimize the 2 norm distance. So you're going to find a point in the set that has the least 2 norm to Z. That will be a projection. Right? This will be the solution. And it'll be perpendicular to the tangent. Right? So x star is really the Euclidean projection of Z to the set. So it's a projection. There are even people saying that proximal operation is just a generalized projection. There are even people saying this thing. I don't agree, but I mean, it has a point. Okay. So first thing is projection to set C. The second one is even simpler. You're going to do arg min lambda over 2 norm squared plus 2c 1 over 2c x minus z 2 norm squared. Is this simple? It's a quadratic. Right? Just take the gradient. So solution x star should satisfy 0 equals lambda x star plus 1 over c x star minus z. And solve for x. It's an average. So x is z over c z over c divided by lambda plus 1 over c. It's some scaling of z. You just scale z. Okay. What about the third one? Third one starts to be interesting. This is interesting. This is not interesting. This is interesting because this function is not differentiable. You minimize the function itself is 0. But how about you do a 1 norm? How about I do a 1 norm? This is 2. This is... Well, first thing, everything is decomposable. Which means this is equivalent to taking the argument of individual component xi plus 1 over 2c xi minus zi absolute value squared. So how many of you have seen this? Huh? Homework. Oh, great. Yes. So, solution. What's the solution? If you have done the homework, I know only like half of people submitted their homework. Huh? Okay. So the way to do this is do a piecewise case by case analysis. You assume the solution is positive, you assume the solution is 0, or you assume the solution is negative, and see what will happen. Okay. So the solution is xi star equals the following: zi minus c if zi is greater than or equal to c, 0 if z is between negative c and positive c, and zi plus c if not otherwise. I mean the zi less than or equal to negative c. Right. No, this is called softest thresholding. There's a name for this. It's called shrinkage or softest thresholding. Okay. Is this homework? I don't remember. Is this homework? This is not differentiable. This is 2 norm without the square. Is this homework? This is not homework. Okay. So what's the answer? So if the groups now these are groups of components of X. So it's X sub in group I. If these groups do not overlap, there's a closed form solution for this. Is this a homework? This is homework, right? 2 norm. You minimize 2 norm plus 1 over 2c plus x minus z 2 norm squared. Is this a homework? No? So what will be the solution of this? Okay, there's no time to analyze it. I'll just tell you the solution. The solution is, let's say we consider 2-dimensional space. I draw a ball. This radius is c. Right. So this radius is c. And if z is here, you're going to move toward. You're going to move toward the origin, but only for length equal to c. So this will be x star. If you're outside the circle, you move toward the origin for a distance c. If you're on or inside the circle, you get 0. If your z is somewhere here, your x star is the origin. There's still something called softest thresholding, except that you're gonna move not component-wise, but you're gonna move together in 2 norm sense toward the origin, move up to c distance. Okay. So if you were to express the solution, this one equals the organine equals z divided by 2 norm of z times the maximum of 0 2 norm of z minus c. And I'm doing this is the solution. Under the convention, 0 divided by 0 is 0. So just in case z is 0, the solution is 0. That's the solution. So what about this guy? Nuclear norm. I mean, if you know, you should say. I mean, I know some of you know. How about nuclear norm? 1 over 2c x minus y, or alright, so when you talk about matrices, this proximal operator is not defined as a matrix 2 norm. Matrix 2 norm is the operator norm. We're going to use the matrix Frobenius norm. You treat the matrix as vectors and then take the 2 norm. Alright. Okay, so it turns out, first thing, you can put any norms here as long as it is unitary invariant. You can put any function of a matrix. If this function is unitary invariant, in other words, you put a unitary matrix here or put a unitary matrix here, you can ignore them. Alright. If this function is unitary invariant, because Frobenius norm is also unitary invariant, whenever you have two things that are both unitary invariant, which means you can reduce it to vectors. I can multiply any unitary vectors here. And essentially reduce this thing to a vector, to a diagonal. And therefore this becomes a vector problem. So in fact, this is just talking about, this is really just doing a singular value operations. You're actually looking at the singular values of this. So you're actually minimizing the summation of the singular values plus 1 over 2c, the singular values of x. This should be summation. The summation of the singular values of x minus the singular values of y to norm. Okay. So you can think this as the L1 norm of singular values. In some very informal way, I'm going to write it like this. And this is just the singular value vector of x plus minus the singular value vector of y. Alright, this is really the problem. So it reduces to the second, the middle problem, the third one. So all you do is you calculate the singular values of y, do a singular value decomposition. Alright, calculate the singular value of y, and then apply the third one, do a so-called soft thresholding on singular values. Alright, so this is you do. Step 1, do y equals to u sigma v transpose. This is SVD, alright? And then look at the diagonals. So let's say a singular value y equals the diagonal is defined as the diagonal of sigma. And then you do soft thresholding. Thresholding. You obtain the singular values of solution x star. Okay. Step 3. You recover the solution x star as the same u multiplies the diagonal. Let me use this. The diagonal matrix using the diagonals sigma x, then v transpose. I just do this. So I can keep the singular vectors, singular factors of y, because both norms are singular invariant or unitary invariant. That's the reason. So I can mimic this, and instead of do soft thresholding, I'm going to do this or that. We can also do that. Let's say if I change this to Frobenius norm squared, or if I change it to Frobenius norm, you should be able to do that. If I change it to the matrix operator norm, you should be able to do that. Matrix operator norm is also unitary invariant. So all you do is do a singular value decomposition of the input y matrix and then operator on the singular values. You keep these factors. This is all you do. Alright, so these are the examples. So no, you see most of the time we're actually doing proximal operator with simple functions. We don't do it with complicated functions. Alright. So, now if you have the solution, the proximal solution of f of x, you can easily derive the proximal operators for these functions. So if you scale a function, you should be able to derive its proximal operator. You scale the function, you actually put this alpha to c. So before we were doing prox c and f. All right. If you put an alpha here, this beta is ignored. It's constant. It doesn't make any difference. So you put alpha here, you're going to put alpha here. All right. Okay. If you scale the input, the same thing. Scale the input, you can. Of course, you're not going to scale this thing, but you can scale something else. But it's very simple. You should be able to do it yourself. If you add a linear function, should be easy. If you add a quadratic function to f, it remains easy to derive the solution for g. All right. Some basic stuff. So in other words, if I ask you to do the proximal operator, instead of doing this, I'm going to ask you to do, say, let's say alpha times x plus a constant matrix B, you should be able to do it. It doesn't make any difference. Okay. All right. So let's move forward. Let's look at more interesting properties of this proximal method. And there's something called a resolvent, which is just a proximal operator. It's the same thing. So here's the points. Subgradient is a point to set mapping. So is identity plus c times subgradient of f. It's a point to set. You pick a point, you get a bunch of subgradients in general. However, in general, if you have this in general, the inverse is also a point to set. The inverse is a point to set in general. However, we claim this is actually the proximal. So whenever I write proximal, it means this. It means the operator that returns me the solution. It means I don't have to write it on the board. It's this. You look at this. This is C. This is a C partial F. You treat it as an operator. Okay. Treat it as an operator plus identity plus x. Identity times x minus z equals 0. No, this is z is here. 0 is in this set. This is a set. I can move z to the right hand side. So z is in this set. And I have argued, if you tell me a z, and I ask you to recover x, there's only a unique x. This x, the solution is unique. Therefore, when I take the inverse, now this inverse is just an operator, all right? So the solution to this equation can be written as identity plus c times partial f inverse z. I do not write belongs to because this is unique. Right. So if you see people write weird stuff like this, it's just a proximal operator. The proximal operator is a resolvent operator applied to z. Okay. A resolvent. So this resolvent is a point to point. So how do we? It's actually, if you write the gradient operator, let's say you're going to get a new point as z minus step size times the gradient, or even a subgradient of z, and this is actually identity operator minus c times gradient operator applied to z. All right, so you can compare this to that. Just two operators. It's just like it's just like 1 minus alpha or 1 over 1 plus alpha. It's the same thing. All right. Moral envelope. I'm probably not going to talk about this. I'll just tell you the bottom line. I don't want to go through everything here. The bottom line is Monroe envelope is a value. It's the value of the proximal operation. Right. I'm not taking the solution. I used to write argument, but now I just write minimum. Infimum means that you may not be able to attain the solution, but in general you can just think it as minimum. So you minimize this function. The minimal value is called Monroe envelope. Monroe envelope is smooth. It's a smoothing of f. Okay, so if you look at f, the input is y. If you look at this problem, the input is x. The input is x. You minimize over y, but you smoothed it. All right. There are a bunch of properties, but the main thing is the gradient of the Monroe envelope is just the proximal. Right. Whenever you take the gradient of Monroe envelope, you can always write it as a simple relation with the proximal operator. Or you have this or that, all kinds of things. But the gradient of the Monroe envelope is related to the proximal. This is the Monroe envelope of the convex conjugate. You can sit down and work out all of these relations. All right, tell you an interesting thing. What is the Monroe envelope of L1? It's a function that has long existed. It's called a Huber function. Some people call it a Huber norm. It's not a norm. This is L1. Right? L1 is not differentiable. Now today we actually love long differentiable functions because they give us interesting solutions. It turns out even minimizing certain long differentiable functions actually makes the algorithm simpler, makes the convergence faster. But for a long time, people don't like these functions. So this is what they do. Instead of minimizing f of x, they minimize Monroe. Let's say c equals 1 norm of x. It's going to be a smoothed version of L1 norm of absolute value. This is the smoothed version. You're going to do a quadratic. Is that equal? Let me see. So the bottom, around this non-smooth point, you're going to do a quadratic. Then it becomes flat and parallel to the original function. All right. This white function is absolute value of f x. This blue function is Monroe envelope of absolute value of x of the absolute value function use input x. So Monroe envelope is just smooth stuff. So the idea is to smooth a closed, proper, non-smooth convex function. There are people who, for example, Nesterov and people analyze. So you have trouble when you minimize the non-smooth function. You usually have some trouble to get a good convergence rate. You will usually get slightly worse convergence rate. But you can smooth it a little bit. Once you smooth it a little bit, this function is differentiable. So I minimize a small approximation of an original function. Instead of minimizing f of x plus something, you're going to minimize the Monroe envelope of f plus something. There are people doing this. This is the approximation of absolute value. All right. Okay. So this is not just one thing. I happen to mention this, and there's nothing. I'm not going to use this. Proximal algorithm. Now, we're doing the algorithm. We actually look at the algorithm. The algorithm, assume f has a minimizer, has a finite minimizer, and the algorithm is very simple. You just plug in f of x, look at the proximal operator with a step size, and get the next point. This is the so-called proximal iteration or proximal point algorithm. All right. This algorithm converges because of one thing. Because this operator has a property called firmly non-expansive. Now, first thing, if f is a convex function, then this operator will never be expansive. Expansive means let's say this operator is t. Expansive means I put t. I look at t of x and t of y. I look at the distance. The distance is greater than x minus y. This is called expansive. All right. Now, if you learn basic fixed point theorem, you know that a contraction. If rho is less than 1, it's a contraction, right? So every time you have 2 points, you get close, close, close. Now, if this point you let y be the solution, and solution. Now, let's say you look for a fixed point. Remember, a fixed point of proximal operation is a solution, right? Recall, a fixed point of the proximal operation is a solution. So you look at you want to go to the fixed point. So you replace this by x star. You replace this by x star. Right? This is your xk, the previous point. After you apply this operation, you get xk plus 1. Therefore, your next point is always get closer. This also equals x star, the fixed point. The next point is always closer to the solution than the previous point by a certain fraction. Therefore, if you have this kind of contraction, you're going to converge geometrically fast. But we don't have this kind of contraction for proximal operator. It's very easy to come up with examples where this inequality doesn't hold, and this inequality actually holds with rho equals 1. If rho equals 1 means you may be able to do something stupid like this. Let's say this origin is the solution. If this is the contraction, it means the distance. This is distance to the current point. Let's say you get a new point. I get a new point here. This length always shrinks. Always reduces at a certain fraction. Next time you're going to maybe go here, but it's shorter. Next time I may go here, but you're actually getting closer to the solution. You're always within a smaller bulk to the solution. But if you are non-expansive, the worst thing can happen is actually I just travel on this circle and never get closer to the solution. It's possible. Okay. But when you add another addition, another property called firmly non-expansive, add this property, you're going to be able to show it converges. Alright. So convergence is not the topic of this lecture. We're going to do a bunch of convergence of different algorithms later. But I just want to mention this. Firmly non-expansive is the reason why proximal point algorithm is going to converge. It's actually converge with a fixed. If you fix for any c, fix ck as any c for all k, you're going to converge. You can also use varying ck. For some reasons, sometimes I can move faster. Sometimes I know I have to move slower. So you can do a different ck. As long as ck, you add up ck, it's not summable. It's summed to plus infinity. All right. Okay. You can also do some weighting between the current point and next point. This is your next point, but you don't use it as the next point. You do some kind of weighting between the current point and next point. This weight doesn't have to be 0, 1. Doesn't have to lie between 0, 1. If 0, 1, it's you take a middle point. This is a current point. This is a proximal point. It takes somewhere in the middle. You can actually extrapolate. You don't have to stop there. You can even go further. You can extrapolate. So this one actually goes from 0 to 2. Now, what's interesting is if f, this function f, is piecewise linear. There's a name for that. It's called polyhedral. This function is piecewise linear. Then you do that, it guaranteed to give you the solution in finite number of steps. converge finitely. You can show this. This is not too difficult to show actually. All right. Okay. This proximal algorithm. There's an interesting interpretation of this algorithm. You just write out the original form of the operator. It looks like this. It's the original form. And I finish this slide. I'll let you have a break. So you minimize over x of this. So this I claim. What it does is the following. I'm going to apply diminishing regularization. This is something called a regularization. If you minimize f, just minimize x to norm squared, you're adding a quadratic to the function. You're adding a regularization. You make it have a better property. But you can't do that because if you do that, you change the solution. Right? Instead, we do x minus always minus the previous point. If your next point is close to the previous point, the regularization, the addition to this function is very small. If xk plus 1 is close to xk, this term has a small value. If xk plus 1 is very different, is very far away from xk, this term has a large value. So as you converge to this point, this actually is smaller and smaller. Therefore, you are applying diminishing regularization. You are giving more weight. Essentially, you're giving more weight to f of x over the time as you converge, and you're weakening this term. You're weakening this term by always plugging the latest point. If you keep a fixed point, you're not weakening it. It's not diminishing. But if you put the latest point, the last point, that regularization is diminishing. Okay. Last point, there are many algorithms. We're going to see many algorithms use proximal of this. Either apply it to the dual or use it as a part of the algorithm. Many algorithms, but not many algorithms directly do this in a primal sense. If you have a function f of x, complicated, you don't usually do this because every step is not simple. You have to minimize the original function together with the quadratic. It doesn't necessarily simplify things, but the benefits is if you have certain non-differentiable, sub-differentiable functions, you're going to do this. Or next lecture, next hour, we're going to look at duality. Now, there are going to be very interesting things you're going to see in duality. I probably let you recall some of the existing algorithms you learned. All right? Okay. So we have a break of 10 minutes.